Well, hello everybody. Apologize for my absence today. I woke up this morning with a headache and a swollen throat, and didn't expect to not be there today. But anyway, let's go through what you needed to learn or what you needed to know for today. Talk to somebody else. Would you rather have no fingers or no elbows? That's an interesting one. Just a reminder that next Wednesday is a Eagle deadline, so anything from Unit 9 needs to be completed by then. Let's start off by having you work, preferably with somebody else, on the left side for number 4 and number 5. Left side's number 4 and 5. These are part of the equilibrium notes that we were working with yesterday. So again, the last two left sides that are part of there. Go ahead and work on each of those, and then we'll come back here and we'll discuss. All right, so on the left-hand side, it asks you to take what you've got in the boxes and draw a quantitative molecular picture supported by calculations. So I'm going to go ahead and I'm going to start this off by just counting the particles. So we've got 12 of this reactant and 12 of that reactant, and we're going to put those together, and then we're going to follow the K to see what percentage ends up in each side at equilibrium. So our K is going to be product 1 times product 2 over reactant 1 times reactant 2. And we need that all to add up to 25, or to multiply out to 25. I've got 24 total particles that I can use, and I know that for every one of each of these that's used, one of each of those is produced. Okay, so that means my P numbers on the top are going to be the same, and my R numbers on the bottom are going to be the same. So if I just start with any random amount, and we also know it's 25, so we know that there's going to be more product than reactant. So if I just start in the most simplest case of that, where there would be 7 and 7 over 5 times 5, right? 12 particles, 24 particles total. That would give me 49 divided by 25, which is nowhere near 25. So I'm just going to keep doing combinations, and you should come up with a combination where you see that 10 of each product molecule and 2 of each reactant molecule gives me 100 divided by 4, which would give me a K of 25. So in the end, we are going to have 10 of this in my box, 10 of that in my box, 2 of those in my box, and 2 of those in my box. All right, our other problem asks us to consider the initial mixture of N2 and H2 that can be presented as follows, and then the gases react to form ammonia, represented by the following profile. Okay, it says label each plot on the graph as either N, H2, or NH, relative shapes of the plots, and when is equilibrium reached. All right, so if these are my reactants to begin here, okay, we know that the reaction is going to be N2 plus H2 goes to NH3. We actually worked with this one yesterday, and so if you balance that out, you get this prospect here. And so you can see that if we're starting off with these two, those must be the green and the blue lines. The green-blue line goes down much more sharply than the blue line does. And so therefore we know that the green has to be the H2. The blue has to be the N2. And the NH3 coming on is our red. Okay. Relative shapes of the plots, again, are based on the stoichiometry that we have down here. Okay, so again, the H2 goes down 3 times as fast as the N2, and the NH3 goes up twice as fast as the N2 goes down. When is equilibrium reached? Again, we know that equilibrium is reached when the rate of the forward and the reverse are the same, which leaves our concentrations about the same, or leaves our concentration of each thing the same. And so where I just drew that blue line roughly, and probably a little bit to the right of that, is where you end up with equilibrium. All right, so I asked you to do problematic problems, 10A. There's our problem set 10A. If you have any questions on that one, please send them to me through Schoology. Take a look at those problems, and I can send you an explainer of those. So the main job for today is to be able to use ice tables to solve for equilibrium concentrations and constants. And so you had a set of notes last night about using ice tables to do just that thing. Hopefully you watched that and you got that taken care of. If there are any questions about that set of notes, once again, please let me know. All right, so with those notes, there was a left side, and the left side looks like this. It says 0.1 molar carbon dioxide gas reacts with 0.100 molar hydrogen gas to produce carbon monoxide gas and water vapor at 900 K. The reaction is allowed to come to equilibrium, and the Kc is 0.640. What are the equilibrium concentrations of all reactants and products? All right, so we are going to go ahead, and we are going to do this left side right here. And we're going to start with the reaction. So we're going to start with R, which is CO2 plus H2, and that reacts to produce CO plus H2O. Okay, so the first thing I want to do is make sure that thing is balanced, and indeed it's balanced just like it is. So that's nice, all one coefficients of 1. So then I start with my initial concentrations. Initial concentration of carbon dioxide is 0.100 molar. The initial concentration of the hydrogen gas is 0.100 molar. And the carbon monoxide gas and water vapor are going to start out as zeros. Okay. All right, change. Okay, as this thing moves forward, that's going to go down by some amount x. That's going to go down by some amount x. These are each going to go up by some amount x, which then leaves us with 0.100 minus x, 0.100 minus x, x, and x. All right, so now that I've got all that filled out, I can now use my equilibrium constant. Kc equals 0.60, which is products over reactants. So that's going to be x squared over 0.100 minus x squared. Okay. Now at this point, I could go through a whole bunch of crazy math to try to solve this thing for x in the normal way. But if you'll notice that we've got both squares on the top and the bottom, and if we've got squares on both top and the bottom, we can undo squares using a square root. So that's what I'm going to do here. And so if I do that, I get 0.800 equals x over 0.100 minus x. Okay, so if I go ahead and now try to solve that for x, I get 0.08 minus 0.8x equals x. Okay, add 0.8x to both sides, so 0.08 equals 1.8x, and divide both sides by 1.8, and I get x equals 0.044. Okay. All right, so if I do that, and I have that way, I can now see that my concentration of CO is going to be 0.044 molar. My concentration of H2O is going to be 0.044 molar. And then for the other side, I'm just going to take 0.1 minus 0.044. And that gives me 0.056. Okay, so that is going to give me a concentration of CO2 of 0.056 molar and a concentration of H2 of also 0.056 molar. Okay, so again, shortcut we did up here that helped us out because we had squares on the top and square on the bottom. But again, sometimes you're going to end up with a quadratic, and when you end up with that quadratic, then you're going to go ahead and use the quadratic formula or your solver on your calculator to be able to work on that. All right, so you have a whole bunch of stuff to do for me for the weekend. Okay, the first one is making sure that your fix-its gets taken care of by then. You can take the notes from last night and do those concentration notes, summary questions on those. Problem set 10B is in Schoology for you, and there are also extra practice problems in Schoology if needed. Okay, so again, this is an if needed. I didn't even assign it as assignment. It's just there if you're like, I'm not quite getting these ICE tables and I need a little bit more practice, you can go ahead and work on those there. The other thing that we are going to have for this long weekend is you are going to go ahead and do lesson 4 for me. Okay, and lesson 4 has already been posted, and we will do a whole bunch of cleanup on things on Monday. So you have the rest of today to work on things. Be productive.